Today's talk is different in two aspects. First, its domain. Its domain is rather unusual. It is mechanical engineering, machine design, how you design shapes. And second aspect that it is different, that it is more about problem definition, problem statement than about solution. Of course, I do have some solutioning towards end of the presentation, but it's more about how a problem gets defined to be solvable. So mechanical engineering and problem definition. These are the two different things in this talk. So let me spend some time about what the problem is, what it is, what is domain, and how it is connected to graph technology. All right. Um, you must have seen these shapes around. And one thing common in these shapes, if you observe closely, they are made of something called a sheet metal, a thin, constant width, thickness material. Like sheet metal is this aeroplane body, the small part, even big construction, they are made up of um, material that is called sheet metal, where thickness is constant and the other area is large. Okay. Why I'm talking about this? Because um, typically, when you design such things, nowadays you don't prepare them first and then test them whether they'll survive the loads and all. We design them in software called CAD, computer aided design. Okay. You design all these shapes in CAD package, and then you take these shapes to another package called CAE, computer aided engineering, where you test it. If you apply load like this, will it buckle? Will it stress? Will it break? All these things, at least the initial stages of design, of designing all these shapes that you are seeing, or many such shapes, you do it on computer design. The modeling part is done, and then you test it in software itself, in CAE. So there is a speciality about sheet metal based shapes. That's what I'm going to talk today. Okay. All right. As I said, CAD is for designing shapes. CA is for the analysis, engineering analysis, meaning stress analysis, strength analysis. Then, when you take these shapes which are modeled, designed in CAD to CA, few things are done in between, because there are a lot of small shapes or holes or fillets in the shapes which are not necessary in engineering analysis. Those are removed. This is called as simplification of shape. Another thing that is done while taking a shape from CAD to CAE, especially in case of sheet metal shapes, meaning which are made up of when thickness is constant, is what is called as dimension reduction. I'll explain what it is. And that's where today's topic is all about. Specific to sheet metal related shapes and dimension reduction. All right. What happens when you are designing shape like this? While doing analysis, you do what is called as meshing, meaning all the shape is broken into small bricks called as elements. Okay. And then load is applied. And then analysis, engineering calculation is done. Whether at this point it will buckle, it will break, it will tear off. All these things are done while doing meshing on the element, per element basis. And that's how we test a shape like this on the left hand side, whether it will survive the load conditions in the practical situation. Okay, so this is meshing. If you can see clearly, when the shape is like this, thickness is constant, the elements are brick elements, meaning solid brick elements. But in case of sheet metal, as I said, or plastic, where thickness is constant, what you do, you create a surface between the thickness, okay, and do surface meshing on it. Meaning instead of 3D brick meshing, you do surface meshing. What's the advantage? I'll show you the advantage. Instead of multiple nodes on each brick, you have to solve for all of them. Computation is more. When you do surface in the middle called mid surface and do surface meshing, number of nodes are less, calculations are less, but results are equivalent. I'll show you the comparison. By the way, you may or may not follow whatever I'm speaking as of now, but just bear with me because this is how we are converting a machine design, mechanical engineering problem to graph-based problem. Okay, so these are some comparison numbers. If you have solid mesh, meaning brick-like elements, for a shape, you need these many elements, these many nodes, and this is the result. The bold thing is result, and it takes 30 minutes to solve because a lot of calculations have to be done. But instead of that, if you create a mid-surface first and do surface meshing, then you can see the element numbers are reduced, node numbers are dramatically reduced, but the results are equivalent and we are saving on time also. So half the computation time and similar accuracy. So this is the advantage of mid surface, especially for sheet metal or thin walled parts. Okay? That's the idea. Bear with me. Now we are coming how we are solving sheet metal problem with a mid surface now. All right, this is a simple example. If you have a solid like this, shape like this, its mid surface looks like this. Can you imagine? It's the surface in the middle and it looks very similar. Hole is there, but thickness is not there, isn't it? So thickness, this is why it is called a dimension reduction. The thickness dimension is reduced. So far we saw for sheet metal shapes, compute mid-surface first, then the computation becomes easy and very efficient. Now the problem is, given this shape, how do you compute this shape? Very difficult problem actually. And research on this problem is going on for 50, 60 years, including my own PhD in this topic. But problem is still not fully solved. Uh, it is solved for some academic shapes. So just one more example for a shape like this. This is the mid surface, and you can see computing a mid surface for a simple slab like shape is very easy. Just offset the shape, offset the top surface or bottom surface. But in case of connections, how do you join the connection? That logic becomes very, very critical and challenging. That's why many CAD and CAE softwares packages have this functionality, but it is not foolproof. So people may have to do manual corrections later and takes ages, many weeks and months to do that. But people still do it because once we get mid-surface, the computation becomes very fast. Then you can do experimentation in different shapes very fast and efficiently, less money. That's why people still do it, even though the mid-surface operation is not foolproof. All right. How is the state of the art? For this part, you can see the mid-surface like this. Can you see a lot of problems? The corresponding surface for this is missing, connections are missing. This is how the current algorithm works. So that's why I took this up as my own research work, PhD work. So this is, as you can see, the 3D problem, solid shape problem. Now, as this is very complex problem, can we dilute the problem a bit? Okay, I'll explain how to dilute the problem. We are still in problem definition zone. All right. We can't tolerate gaps because, yeah. So for a shape like this, we can see a latest, so-called latest. I did this research a couple of years back. So this was the state of the art that time. You can see a lot of problems here for even simple shape like this. I've taken English letters because it's easier to imagine the mid surface, right? That's why I've taken them. You can see one more example. For a simple shape like K shape, the connections are not done. So this is a big problem in the mechanical design industry. And we are trying to address. One more example, the current quality. A lot of these 3D shapes, sheet metal shapes, are made up of operation called sketch profile first and then extrude. Right? This is how you make sheet metals like this, isn't it? So a mid surface for a shape like this is nothing but mid curve of this sketch profile extruded. Let this statement sink in. A mid surface of the whole shape, this gray, dark gray thing, is nothing but you take this sketching profile which got extruded to make this shape, take a mid curve of the yellow profile, okay, and then extrude it, isn't it? That's how now the problem has reduced from 3D shape mid surface to 2D shape mid curve. Are you getting it? That's what the idea is. Now we are changing the problem or diluting it a bit more. Now the problem remains, given the yellow profile, which is 2D, planar, how to compute a mid-curve? Isn't it? That's the problem now. And we are trying to solve this problem. Just a simple example. Uh, what is mid-curve? For black profile like this, outer profile, how to compute a red mid-curve? Another shape, L shape, very simple to imagine, easy to imagine. For outer black shape, how to compute this? Now you would say, why it is not such a it is not a difficult problem, right? Just offset. Just imagine you're writing an algorithm. You're getting list of lines or points or whatever. You don't know which is the thickness line, which is the longer line, and this shorter and longer is very relative. It's not an easy problem to solve. Again, as I said, this research is going on for 50, 60 years now. Uh, there are many approaches. One is called as medial axis transform, chordal axis transform, thinning. Thinning is very easy to imagine. You just go on offsetting everything. Wherever the offsetting stops, that's the midcurve. But you can see there is issue. This portion is missing. Lot of such things. There's another pairing approach. My PhD is about this approach. Anyway, but as I said, I did it rule-based way, proper algorithm way. So this is just the history of the problem. 1967, almost what, 50, 60 years plus is going on to solve this problem. This is my own work for this shape. This is the midcurve. So for academic shapes like this, I did get good results, and I'm showing only the good results here. The ones that did not work, I'm not showing. Yeah. So my implementation, my algorithm of computing midcurve was rule-based. It worked for very simple shapes wonderfully, but whenever a new shape came, then you have to tailor the algorithm. So it's not scalable. That's why actually I did not work on, I worked only on rule-based approach in my PhD, but later, once my PhD got over, I thought I should tackle it with deep learning because it will generate the logic, it will generate in abstraction the algorithm itself, the learning part of this transformation from profile to its midcurve. Can it learn? That's what I was thinking. And we are trying to solve this problem of midcurve computation using deep learning now. But the problem is how to define these shapes. For numerical data, it is easy because you have vector of numbers, right? Input and output. But how do you define shapes so that it becomes numeric to be given to neural network, right? That's the idea. Um, and of course, we will need a lot of shapes and their midcurves because if you are trying to solve it using machine learning or deep learning, we need a lot of training data. So these are the issues that I was wondering if deep learning can solve, right? So you have to give numbers here. Even in case of NLP, natural language processing, you cannot pass text here directly. You have to convert them to word embeddings, document embeddings, which then gets processed in the neural network, isn't it? So how to convert shape to vectors? That's the problem. So The problem now is given 2D closed shape, find its midcurve. Simple. Input is what? Set of points. For simplicity, let's assume it's a simple shape, maybe linear shape for now, just lines, not curves as of now. And output is the red shape that we saw, right? So this is the problem. We are slowly coming towards graph now. We started with sheet metal shapes, 3D shapes, 2D shapes, mid-curve. Now, right, how to solve mid-curve problem using neural networks. Now, if you can imagine, this problem can be modeled as graph-to-graph problem, isn't it? Let me just go back and show you. This is the middle of the talk now. If you see this shape, this shape, this is nothing but nodes, right? These vertices are nodes of a graph, and these lines are edges, arcs between the nodes. One more difference actually in graph, it's all topological connectivity, meaning topology. It's only topology connectivity. It does not matter whether this node is placed here or here, but in this case it matters because it's the position of a vertex. So it's more than a graph, I would say. Graph plus geometry. I would call it network for now. So this is a graph problem, isn't it? Nodes, edges, nodes, edges, nodes, edges. This is the input graph. And what is the output graph? What we want from this transformation? The middle one, these two lines. So this is input graph, this is output graph. This is input graph, this is output graph. Can you notice the problem? Generally, in case of, say, a similar problem would be machine translation, right? English to French. Sentences are there. You supply lots of data. So you employ encoder-decoder networks. Wherever the sizes are not matching, you put padding and you solve this machine translation problem. That's not going to work here because even if you have just points here, the topology between input and output is very different. It's typically reduced number of nodes, reduced number of edges, their positions are different. We cannot do padding also because if you add 0, 0 padding coordinate, it becomes part of the shape. So padding is also not problem. So it becomes a very difficult graph to graph problem. And I personally did not find any encoder decoder architecture where graph to graph neural networks are available. Typically, neural networks in GNN, graph neural networks are available for node class prediction, link prediction, but or graph class prediction, but graph transformation architectures I did not find. So this is the problem I wanted to highlight in this conference. So as I said, this talk is about a different domain, mechanical engineering, and about a problem definition itself. Can we solve, do we have a graph neural network which takes input as a graph, output as a graph, but with different topology and geometry? I can give you hundreds of such pairs, but there is no architecture that supports a back propagation like this in my survey. So what did I do? I did not stop. I converted this unsolvable graph problem to a rather solvable thing. And I'll explain that quickly. Yeah. So I considered, so there were issues like different lengths, different coordinates. How do you solve that? I solved it by making this problem as image to image problem. Can you imagine? So if I take image of this, uh, black Y and red Y, 28 by 28, 100 by 100, then it becomes a fixed size problem. And there are lots of architectures available for image to image translation, isn't it? Pix to pix, units are available. So I tried solving this problem by image to image. Like so, this is the input shape, input image. This is the output image. Input image, output image. You supply hundreds of such pairs, and a pix-to-pix network or simple encoder-decoder network also will solve it. All are numbers, so all are numerical things. So for shapes like this, We can have an encoder-decoder network, original input or is reconstructed input. So this is the way encoder-decoder will work. This is input shape, this is output shape. Right? This is how original mid-surface Midcurve problem has been taken to image land now, because we could not solve it in the graph land. So I'll just quickly show the results. Lots of data was prepared. It's easy to augment the data because you can just move the both things, input and output similarly, and a new pair is created. It is very easy. So lots of transformations were used. So for shapes like this, these are the mid-curve, these are the profiles. This is how I generated a lot of data. I tried a simple encoder decoder, many architectures. I'll just show you example of one such result. Result is not bad, not very good also. Some stray points are there, but this is how you could generate a mid-curve for a profile, isn't it? This is how it was done. Another thought that and the research on this topic is still going on, just to have a very clean output. Another thing that I did was, instead of converting shapes to images and then solving, can I serialize shapes to a language, to text, like a JSON? Points are like this, midcurves are like this. Then it becomes text to text problem, which is solvable by very famous, the current in thing, generative AI, large language models. So this is what I tried. I'll quickly show and then probably open up for questions. So now, instead of graph to graph, geometry to geometry, instead of image to image, now we are into text to text, language to language model. And how do I represent a shape? I'll quickly show. This is how I represent I shape. Profile is like this. These are points. Midcurve is like this. Profile B-rep is a specific way of representing this. It's called B-rep, meaning boundary representation. You have list of points, segments, and then multiple segments, loops, and other things. This is how I define shape in terms of text, JSON basically. And this is input JSON profile. This is output JSON. If I give hundreds of such pairs, can large language model on its own by few shots or by fine tuning unseen profile period. That's the idea I toyed upon, and I'll quickly show the result. This is how I generated data, profile BREP and its corresponding midcurve BREP. Using this, I fine-tuned open source language model, and I'm showing you the results now. You can do few shots also, as I said, and then ask for the unseen point list. But you can do fine-tuning also. In few shots, I use that time currently available ones, and the results were not encouraging at all. These guys could not interpret the geometry well. Then, of course, I did fine tuning, and then this is the way it is done. The results are still not encouraging, but I'm trying to build more on this, and probably in coming days, I'll have a research paper on this. All right. So this is I wanted to cover. As I said, I showed the solutioning part towards end, but the idea was how to convert a machine design, mechanical engineering problem to graph related. Thank you.